Just like we had a formula for the partial sums of an arithmetic sequence, we have a formula for the partial sums of a geometric sequence. We're going to develop the formula now, and this is actually one of my favorite calculations in a math class. So I hope you enjoy how this formula is created because it uses a little bit of creativity. So first, we know that the nth partial sum is the sum of the first n terms. So that's going to be a plus ar plus ar squared plus ar cubed all the way up to ar to the n minus 1. Remember that the nth term of a geometric sequence is given by a times r to the n minus 1. Now what we're going to do is we're going to multiply both sides of the equation by r. So on the left that gives us r times s sub n, and then on the right we've got ar plus ar times r is ar squared plus ar squared times r is ar cubed plus ar to the fourth, etc., all the way up to ar to the n. We've just multiplied each of these terms by r on both the left and the right-hand sides. Now we actually have two different equations, and we're going to take the difference. So we're going to take the first equation and we're going to subtract the second equation from it. When we do that on the left, this gives us s sub n minus r s sub n. And then on the right, when we subtract, there are a lot of things that cancel. The ARs cancel, the AR squareds cancel, the AR cubes cancel. There's going to be an AR to the fourth that cancels. And this AR to the n minus 1 is going to cancel with a term down here that's inside the dot dot dots. And all that's left on the right-hand side is going to be the a from the first equation minus ar to the n from the second equation. Remember, we were subtracting the second equation from the first. Now, we are able to factor on each side. On the left, we've got s sub n times 1 minus r. And on the right, we can pull out an a and write this as a times 1 minus r to the n. And remember, our goal was to figure out a formula for the nth partial sum. So to get this alone, we divide both sides by 1 minus r, and this gives us s sub n equals a times 1 minus r to the n over 1 minus r. And this is the formula for the nth partial sum of an arithmetic sequence with a as the first term and r as the common ratio. It's really a neat calculation with all of the cancellation and the factoring and whatnot, and it gives us a nice formula that we can use to find partial sums of geometric sequences. So now that we have this formula, let's use it to do a couple of quick problems. Let's find the sum of the first 5 terms of the geometric sequence (1, 0.7, 0.49, 0.343, etc. So we're told that this is a geometric sequence. We can quickly test that the first few terms we're given satisfy this. The common ratio here is 0.7. Every time we multiply by 0.7, we get to the next term. So in this case, a is equal to 1, and r is equal to 0.7. So if we want to find the sum of the first 5 terms, what we're looking for is S sub 5. So it's going to be A, which is 1, times 1 minus r to the n. So that's 1 minus 0.7 to the 5th, all over 1 minus r, which is 1 minus 0.7. If we use a calculator, we can raise 0.7 to the 5th power, and we get 0.16807. And then in the denominator, 1 minus 0.7 is 0.3. And if we use a calculator to evaluate this, we end up with 2.7731. So that is the sum of the first 5 terms of the geometric sequence. It might not be less work to use this than it would be to add up the first 5 terms. We'd have to find the 5th term. But if we were asked to find the sum of the first 100 terms, for example, this would certainly be much quicker. So there are some situations where knowing this formula is incredibly helpful. Let's take a look at one more problem that we can use this for. Let's find the sum of the sum as k ranges from 1 to 5 of 3 times negative 2 to the k power. So we know that this represents a sum, and we actually could write out what the terms of this are. We've got 3 times negative 2 to the first, plus 3 times negative 2 to the second, plus 3 times negative 2 cubed, plus 3 times negative 2 to the fourth, plus 3 times negative 2 to the fifth. But instead of going through and doing all of that out, we recognize that these are the terms of a geometric sequence. The first term is negative 6. So in this case, our A is negative 6. And then the common ratio is negative 2, because for each subsequent term, we're multiplying by another factor of negative 2. And so if we want to find this sum, it will be the 5th partial sum. And so we have A, which is negative 6, times 1 minus r, negative 2 to the n power, which is 5, all over 1 minus r, 1 minus negative 2. Now, negative 2 to the 5th power is negative 32, and 1 minus negative 32 is the same as 1 plus 32, which is 33. And then in the denominator, 1 minus negative 2 is the same as 1 plus 2, which is 3. 33 divided by 3 is 11, so we've got negative 6 times 11, which is negative 66. And this is actually fewer calculations than we would have had to do if we had done it straightforward like that. And furthermore, if we were looking at the sum from k goes from 1 to something like 8 or 12 or 50, this certainly would be the faster method.